Well, hello and welcome back to another episode of Quantitative Bites. It's great to see you all. I hope you're doing well. So today I want to talk about something a little bit different to anything that we've talked about so far, and I want to talk about gradient descent optimization. So this is a numerical way of finding the minimum of a function or minimizing a particular function, and it has applications in a variety of areas, such as in machine learning, where it can be used as a technique to find the coefficients and weights required for a particular neural network, for example, and it has other applications as well. Personally, I'm interested in developing this because I want to use it to do image registration, which is something I hope to go on to look at in subsequent videos. And today, what I want to look at is the theory and some of the mathematics behind gradient descent. So in contrast to some of my previous videos, what I've decided to do is to split this across two separate videos. So in this first video today, we're just going to look at the theory, and then in the second video next week, we will have a look at the code in C++, how we would go about actually writing a practical and usable implementation of gradient descent. But today, I want to focus mostly on the theory. So just before we jump into that, I just want to say, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. I do try and make a video roughly once a week. I just recently haven't quite been able to achieve that, but I'm hoping to get back to it. So if you subscribe, then you don't need to worry about missing anything. Thank you very much. Okay, without much further ado, let's jump right in and have a look at gradient descent. So the theory of gradient descent is actually really not that complicated, but it is worth spending a little bit of time just to look over it to make sure that we really understand everything that's going on before we move on to actually looking at how to implement the gradient descent algorithm in code. Now I want to start with a very simple example that is going to be familiar to quite a lot of people out there, I should think, and this is of course the very basic quadratic function y equals x squared, or as I've written it here, f of x equals x squared. So our function of x is simply equal to x squared. And we've plotted that function here for every value of x between -2 and +2. And as we can see here, the plot in blue, we get the classic quadratic curve. And as we know, is well known, and as we can actually see with our eyes, of course, the minimum of this function occurs when x equals 0. Now, of course, given that we know exactly what this function is, we know this function is differentiable, and we can actually use analytical methods to calculate the location of the minimum. So we know that f of x is equal to x squared, so f prime of x, that's the first derivative of f of x, is going to be equal to 2x. That's simply using the classic nx to the n minus 1 way of doing differentiation. So that tells us that the gradient of this curve at any point is equal to 2 times the value of x. Okay, so for any value of x, the gradient is going to be double that value. Okay, so if x was -1, then we know the gradient is going to be equal to -2. And we can take the derivative of that, which gives f double prime of x, so that's the second derivative now of f of x, and that's simply equal to 2 everywhere. Now, if we solve this equation here, f prime of x equals 2x, it's obvious that that's going to have a solution when x is equal to 0. So when x is equal to 0, f prime of x is going to be equal to 0, and we see that f double prime of x at that point is going to be 2, because f double prime of x, or the second derivative of f of x, is simply equal to 2 everywhere. We have the solution to the first derivative here, which occurs at x equals 0, and we know that the second derivative is positive at x equals 0, and therefore that must be the location of the minimum. And we can use that analytical method for any situation where we have a function and we know the function, we can write it down analytically, and we can use these analytical techniques to calculate the location of the minimum, or indeed minima, if there are more than one. So that's really simple, but then if we can do that, why do we need to use numerical methods? Why would we ever need to use numerical methods like gradient descent in order to find the minimum of functions? Well, the problem comes if we have a situation like this. So in this case, we have what is essentially a black box, although of course in my case the box is blue, but black box is the standard term. We have input, and as input some values of x, and we have as output some values of y, and we have absolutely no idea what f of x is, so we have no idea what's going on in between. So if we don't know f of x, how do we find out the value of x that gives the minimum value of y? Now this is actually a really important problem and crops up in various fields where we need to find minimum solutions, need to find the minimum set of parameters, for example. So this may crop up in machine learning, training neural networks particularly, where you want to minimize, you want to find the set of parameters that minimizes some cost function, or in other areas such as image registration and all sorts of problems where we need to find a solution or value of x that minimizes the output of the result of f of x, but we have no idea what f of x is. So what do we actually do in that kind of situation? Well, the answer is to use numerical methods such as gradient descent to estimate x hat, so the estimate of x that minimizes f of x. So let's talk about gradient descent specifically. So this is the equation on which gradient descent is based, and this simply says that x of n plus 1 is equal to x of n minus gamma times del f x of n. So what does this really mean? So starting from any starting point, so let's consider this. So starting from any starting point x of n, we're going to calculate what our next location of x is going to be, x of n plus 1. And we do that by simply subtracting gamma, that's some constant, multiplied by the gradient of f of x at the point x of n. Okay, so let's just have a look at what that is. So we pick some starting point x of n, we compute the gradient at that point, which here is represented by del f x of n, so we calculate the gradient, and then we can use that to calculate the next point of x of n using the negative of that gradient multiplied by gamma, our constant. And then we simply iterate steps 2 and 3 until we reach some particular threshold, that indicates that we're close enough to what we consider to be the minimum. Now gamma controls the step size, and this is sometimes called the learning rate. So in machine learning circles where they talk about gradient descent, they would refer to gamma as the learning rate, but I'm going to refer to it more as the step size because it controls the step size, as we will see. So what we're going to do, let's look at this example again, a very simple example of the quadratic, and we're going to just work through how we would actually apply gradient descent to that. So the very first thing that we're going to do is we're going to pick a start point, which you can see here. So I've picked a start point of xn equals minus 1. Okay. We then compute the gradient at this point, so that's del f x of n, and we know from the previous slide, of course, this is y equals x squared, so the first derivative of that is 2x, so we know the gradient at any point along this graph is equal to 2x. So in this case we know that x is minus 1, so the gradient del f x of n must be equal to 2 times minus 1, which is of course minus 2, so the gradient here we know is minus 2. And that means we can calculate the location of the next point, x of n plus 1, by taking our starting point, x of n, and subtracting gamma multiplied by minus 1 times minus 2. So minus 1 is the first value of x, multiplied by minus 2, which is the gradient at that location here. And then we multiply that by some value of gamma. Now in this example, I've used the value of gamma that was 0.2. So we have here 0.2 multiplied by 2, which is of course 0.4. So we have x of n plus 1 equals x of n minus 0.4, which of course gives us a value of x of minus 0.6, which we can see here. And then we would simply repeat that process again. So we calculate the gradient at that point, and then we feed that back into this equation along with the new value of x, and it gives us that next location that we want to consider here. And we simply keep doing that until, as I say, we reach some kind of stopping criterion, and then we take that as being our approximation of the minimum. So how do we actually compute the gradient? The problem is we don't know what f of x is. So, of course, we have to estimate the gradient numerically. When we knew f of x, we could easily differentiate it analytically, and then we know the gradient everywhere. But of course, if we can do that kind of analytical analysis, then we don't need to use numerical methods at all. So the whole problem then becomes kind of irrelevant. So we can't calculate the gradient of f of x analytically. So we have to make some kind of numerical approximation of what the gradient of f of x would be. And we simply do that using this equation here. So we have f hat prime, so that's the approximation of f prime of x, is simply equal to f of x plus h minus f of x all over h for some small value of h. And this is, of course, the classic way of calculating a numerical gradient. And we just pick some small value of h, and then we can just use that, and we can use that then this equation to calculate what the gradient would be, the approximate gradient, at any particular location of x. So let's have a look at this. So going back to our quadratic example, we have f of x equals x squared, and a value of gamma is equal to 0.2. At the first iteration, we have our starting point here, of course, xn equals x1 really equals minus 1. And what we're simply going to do is simply iterate over that. So as we saw in the example before, the first step takes us to here, x of minus 0.6. And then we simply keep going, and we see that after 10 iterations, we do indeed reach the minimum of x equals 0. Now, the one thing you'll notice is that the step size changes with every step. So what's actually happening, of course, is gamma is constant, but it's essentially just a scaling factor for the gradient. So the amount that we're moving in x each time is proportional to the gradient of our function at that point. So where the gradient is steep, we descend really quickly, so we take a big step here, and we descend really fast from there, and then we descend more slowly from there to there, and we descend more slowly from there to there, and so on. And this is really where the method gets its name from, because what we're doing is simply descending down the steepest gradient of our function. And of course, because of the way that the equation is written, it won't tend to go back up the other side. It will indeed settle around x equals 0. So we can see how it works, and this is the basis of the common analogy. People often try and describe gradient descent in terms of someone trying to walk down a hill or a mountain without knowing which way they would go, and the analogy goes that they would, from their starting point, simply head in the direction of the steepest gradient for a certain distance, and then would stop and see which would be the steepest gradient from that point, and then head in that direction. Speaking from experience as a hill walker, I would not personally try to descend a mountain that way, and I really would not recommend, if you ever find yourself up a mountain and for some reason don't know the way back down, do not try and do it that way because of the extreme danger of walking off a cliff. However, of course, in this particular example, it really doesn't matter. So there are some caveats to this method. Now, the first one is that obviously we have to choose a value for gamma. Now, I've chosen this value of gamma here for 0.2, which I know happens to work very well for this example. But what happens if you were to choose a value of gamma that was too big? So let's make gamma equal to 0.9, and let's consider the example again. So starting from the same starting point, x equals minus 1, let's see what happens now with gamma equals 0.9. So you see our first step now is massive. So we've taken 0.9 multiplied by the gradient there, which is of course 2. So we're getting a massive step now, which puts us all the way over here. And then our next step is also very big, and the next step is very big. And you can see what's happening. This will still converge to the minimum because it's a well-formed problem. But you can see even after 10 iterations, we haven't reached the final solution. So we can see that when gamma is too big, in some cases such as this, we will still eventually reach our optimum solution, but it's going to take rather more iterations than necessary to do that. And indeed, in some other cases, for other functions, we simply wouldn't converge to the minimum at all. Similarly, if we were to make gamma too small, the problem doesn't work. So in this example here, we've put gamma equal to 0.01, and starting from exactly the same point again, x equals minus 1, we see what happens. You see now our steps are really very, very small indeed. So after 10 iterations, we're nowhere near the actual minimum at x equals 0. If we were to keep iterating this, we can see that this would eventually probably get here. But of course, as the gradient levels off towards 0, so that our step size gets smaller and smaller. And you can see that this would take a very, very long time indeed to converge. So what we can see from that is that it's very important to choose the correct value of gamma to suit the particular problem that you're trying to solve. Now, there are various ways of doing this quite intelligently. There are things like line search algorithms and so on that you can use to calculate the value of gamma at every step. And that's a little bit more advanced, a little bit more sophisticated, and therefore isn't something that I really want to talk about today. I really wanted just to keep this very simple for the moment. So keeping it simple, one of the issues that we face is we do have to be a little bit careful with our choice of gamma. But if we understand something about the particular problem that we're trying to solve, that shouldn't really be too much of a problem. Okay, so this is a slightly more interesting function than the one that we were looking at before, which was of course just a simple quadratic. So here we have a quartic function given by f of x equals x to the 4 plus 2x cubed minus 6x squared plus 4x plus 2. And in this example, I've chosen a value of gamma equal to 0.01. And I picked a starting point here, x of minus equals minus 4, which gives a value of y, as you can see here, close to about 20. And you can see the starting point marked on our plot here. So let's have a look what happens as we iterate through the process of gradient descent just as before. Well, we see our first step, even with a small value of gamma, takes us actually very close to the minimum, which is extremely convenient. So of course the gradient here is very steep, so even with a very small value of gamma, our first step is going to be very big. And then we see our subsequent steps now, which are a lot smaller because the gradient has changed enormously. And we see that very comfortably by our 10th iteration, we have reached what would be a good approximation of the minimum of this function. So that's all very straightforward. Now, this function has one other particular characteristic that neatly illustrates another problem with the gradient descent method, and that is the problem of local minima. So gradient descent is really only valid for convex functions, that is functions that have just one minimum, or at least locally convex functions, so depending on where you pick the starting point. So when we picked our starting point over here, minus 4, we see we do indeed converge to the minimum, so everything is fine. However, what would happen if we were to pick our start point over here? So this is the problem of local minima that occurs. So here we've picked a start point now of x is equal to about 2.5 plus 2.5, and let's watch what happens now as we iterate over 10 iterations of the gradient descent method. Well, as we can see, we're heading in the right direction with the first step, that's fine, but now our gradient has become very small, and we're taking now really very tiny steps indeed, and by our 10th iteration we are nowhere near the global minimum. And in fact, depending how this function is written, there is actually indeed a local minimum, or at least a point of inflection here, to which the gradient descent method will converge. Now obviously if we were to choose a larger value of gamma, it's possible we could get a step that would go over that to somewhere about here, and then we would descend. But it is at least a neat, I think quite a nice illustration of the problem of local minima. So there are two particular limitations or aspects of gradient descent that we have to be very careful about. We have to be very careful about choosing a value of gamma, so that depends very much on the particular problem that we're trying to solve. And we also have to be very careful with our starting point, particularly if we're dealing with functions that may have local minima or that we're not interested in. So our starting point and gamma values really quite important. However, that might sound like two problems that would make this method entirely useless, but that's really not the case. Gradient descent can still be very useful, even in this very simple limitation, as we will come to see in subsequent videos. Okay, the one last thing that I wanted to talk about, and one of the really great things about gradient descent, is that it is easily extensible to multiple dimensions. So all of the examples we've been looking at up to now are single dimension functions. So we have just one degree of freedom, x, and we have some function f of x of that. But of course, we can actually just simply replace x with a vector in the equation for gradient descent. So here you can see x is in bold, and we've gone to a capital F now for the function. So x is now a vector, and we can actually have as many dimensions as we want. And we can expand that, as you would see here. So we have some vector here of n plus 1, we have x1, x2 down to xm, is equal to the same vector at location n minus gamma multiplied by the partial derivative of f of x of n for each one of the particular dimensions. Now, this is the important thing. The only thing that changes when we extend to multiple dimensions is that rather than simply differentiating the function at the particular location, we now take the partial derivative of the function with respect to each specific degree of freedom. So for x1, the first element in the vector of x, we take the derivative of f of x of n with respect to x1. For x2, which is the second element in the vector x, we take the partial derivative of f of x of n with respect to x2, and so on down to the nth element of x, we take the partial derivative of f of x of n with respect to the nth dimension of x. So although this might look a little bit complicated, actually in reality it isn't at all difficult to implement. All that we have to do to calculate the partial derivatives is to simply, for example, if we wanted the partial derivative of f of x of n with respect to x1, then we simply hold all of the dimensions apart from x1 constant and simply take the derivative in this particular direction, and we can simply repeat that for all of the elements. So that's actually quite straightforward, despite the fact that it might look quite complicated. So let's have a look at a two-dimensional example. So 2 dimensions, of course, relatively easy to show on screen. More than 2 dimensions obviously becomes much more difficult to illustrate. So a 2-dimensional example, I think, will serve the point. So we have a very simple function here, f of xy is equal to x squared plus xy plus y squared. And I'm using here a gamma value equal to 0.1 that I know actually works quite well. And we can see plotted here, this is our 2-dimensional function, so we have our values of f plotted over x and y. And we can see intuitively that this function is going to have a minimum at x equals 0 and y equals to 0. That's when this will indeed be equal to 0. So we know the minimum should occur somewhere about here. Now, let's have a look at what happens when we iterate over our gradient descent method exactly as we have done before. We are starting from here, by the way, of x equals to 5 and y equals 5. So that gives our starting point here. So after our first iteration, we've moved to here, and then the second, third, fourth, fifth, sixth, seventh, and so on. And we see by iteration 10, we are actually coming quite close to the location of the minimum, and we can see we can get a very good approximation of the local minimum. So we've discussed the basic principles of gradient descent and the very basic principles of how it works. We've talked about its great advantage, which is the ease with which it can be extended to multiple dimensions. And really, when it comes to solving numerical optimization problems, that's one of the really key features of gradient descent, is that we can work across n-dimension functions really very easily. And we've also talked about 2 of the limitations of the method, which are that we have to be very careful with our choice of the value of gamma. It's quite problem specific. And we have to be quite careful with our choice of starting location as well. And we've also touched on the fact that really the method is only valid for functions that are convex, which means functions that only have one local minimum. Those caveats aside, gradient descent is a tremendously useful method for minimizing or finding the values for which a function will be minimized when we don't know necessarily what that function is. Okay, so that's really everything I wanted to talk about today. We've had a look at some of the theory behind the gradient descent technique. I've talked about some of the mathematics behind it, and we've looked at some examples. And I hope that will be enough to give you at least a broad overview of how the gradient descent algorithm actually works and what it is and why we might want to use it. So in the video next week, I want to move on to having a look at how we would actually create a practical implementation of this technique in C++. That really just leaves me to say that I really hope you've enjoyed this video. It's been a great deal of pleasure making it. If you have liked it, please remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Anyway, listen, it's been a pleasure, and I really look forward to seeing you in the next video. Thank you very much for watching. Bye.